Hello, in this video I'm going to solve question 4, Problems Set 2, Lecture 3, Lectures in Elementary Number Theory. Determine all natural numbers n for which n squared plus 1 divides 4n minus 2. Pause the video at this point and give it a try. Okay, so let us solve this problem. Here, the strategy is this. From the experience probably you got from the previous problem, you know what probably to do. Yes, you want to do something that on the right-hand side, you get a fixed number. Because if you get a fixed number here, for example, let us say 5, 7, 8, whatever, you know that the number on the left is a factor of the number on the right, so then you know what are the possible values for n squared plus 1. So that is the goal. But here you have n squared, here second degree in n, but this is the first degree in n. Okay, what I will do, I will multiply, because you know that we learned in the lectures, previous lectures on this playlist, that if I have a dividing b, and if m is an integer, I can either, if I want to, multiply both sides by that integer m. If this is true, this will also be true, but I can also multiply one side of it, provided that one side is the right-hand side. So I can keep a the same and just multiply the right-hand side by m. Both of them are correct. So here, there is no point to change this. I want to change this in a way that this becomes second-degree polynomial. Okay, the first thing that comes to mind is to multiply the right-hand side, for example, by n. Then it gives you 4n squared minus 2n. Another extra n will appear. So to think a little bit more efficiently, I want to have n squared without having n, because n will also make some troubles for me. So then if you put these together, it is not hard to see, it is better to multiply the right-hand side by the conjugate of the right-hand side. So this means that from here, I can conclude that n squared plus 1, according to this theorem, second part, divides 4n plus 2 multiplied by 4n minus 2. So if this is true, this is also guaranteed. But now look, if you multiply these two, so I can conclude that n squared plus 1 divides, this becomes 16n squared minus 4. Okay? But now it is easy to get rid of n squared without having to tolerate the existence of an extra n here. How? There is a theorem that we learned in lecture 3 that if I know an integer divides another integer, I can add any integer multiple of the left-hand side to the right-hand side. So this means from here I can conclude that a divides b plus, for example, m as an integer times a. Okay, so if you grant me this, I can immediately conclude this if, of course, m is an integer. Okay, so I want to use that theorem. So let me put a pair of brackets. So from here, I want to give the role of that a to n squared plus 1. I want to give the role of b to 16n squared minus 4. And I want to give the role of m to negative 16, because my goal is to get rid of this n squared on the right-hand side. So this means that n squared plus 1 divides 16n squared minus 4, okay, minus 16 times this expression. Okay? First of all, I want you to understand that this is valid exactly because of that theorem. I have chosen that m in the theorem to be minus 16. But why it is good? Because now I can go forward and then copy and paste the left side, n squared plus 1. And on the right-hand side, I can open up the pair of brackets. So 16n squared there and minus 16n squared here are gone. And I have a minus 4 and a minus 16, which becomes minus 20. But then immediately I can know what are these numbers, because this should be an integer for which minus 20 is divisible by. I do not have that much options, yes? So n squared plus 1 is either minus 1 or plus 1. the factors of minus 20, integer factors of minus 20, minus 2, 2, minus 4, 4. These are the possibilities that I can have. Minus 5, 5. And finally, no, sorry, minus 10 and 10. And finally, minus 20 and 20. Okay, so these are the only possibilities. Okay, I can find them. So if that is the case, n squared plus 1 cannot be minus 1, cannot be minus 2. So none of the negative numbers are acceptable because n squared is non-negative. So all of them are not acceptable, okay, because they will not give rise to an integer n. But what about here? If n squared plus 1 is 1, n becomes 0. If n squared plus 1 is 2, I have two answers for n. N squared is 1, so n becomes plus 1 minus 1. If n squared plus 1 is 4, n becomes square root of 3 or minus the square root of 3. If n squared plus 1 is 5, n becomes 2 or minus 2. If n squared plus 1 is 10, n becomes 3 or minus 3. And if n squared plus 1 is 20, n becomes the square root of 19 and minus the square root of 19. Okay? But what I am looking for, let me see. I am looking for all integer numbers n. So if you see, the question was all, natural numbers n. So which one are natural? So n, 0, because in my lessons I told you that I will not consider 0 to be natural. So I take it off from my list. These are not natural numbers, so let us take them off. Yes? And these are natural. But be careful. That's a mistake if you immediately accept all of them. Might be all of them are acceptable, but I want you to understand this is not guaranteed. Why? Because you know that my goal was to find all natural numbers n for which n squared plus 1 divides 4n minus 2. What I did these mathematical legal calculations, and finally I reached to this step and I start solving for n from this relation. So if you ask me what did I find, I will answer you I found all possible answers to this relationship, okay, which makes this one true. But be careful. This statement and that statement in the beginning are not equivalent. For example, is this statement reversible? In other words, can I go backward? If I grant you this, can I go backward and I conclude this? The answer is yes, because you can write minus 20 in this form. That is correct. So you can go from that to here. Can I go here from this one to that one? There is no guarantee. Yes, that is also guaranteed, because you know that that one is double-sided. You know, if A divides B plus MA, A is the left-hand side, M is a multiple of the left-hand side. If I want to, I can eliminate that. In lecture 3, we saw that this is also reversible. So if this is granted to me, I would say that, okay, this is a integer multiple of the left-hand side, I can eliminate that. So that one is also reversible. So that one is indeed equivalent to this one, and this one is indeed equivalent to this one. Can I go backward? Again, the answer is yes, because 16n squared minus 4 can be simply written in this form. But the point is that this one is not reversible. So if I grant you this, you cannot jump and conclude that this one has to be true as well. Okay? So because of this arrow not being reversible, the last statement there and the first statement that I want to solve for it, for n, are not equivalent. But whenever this is true, that one is also true, because in that direction it was logical. So this means that if I am looking for the answers for this, I don't need to look somewhere else. The answer to that one is also among the answers to this one, but not necessarily the other way around. So that is extremely important to check if these answers are indeed true. But this is you might say that, okay, if I want to do a trial and error, why should I solve something? Be careful. Potentially, I have infinitely many possibilities in front of me, because I have to check more or less all natural numbers here to see which one works and which one does not work. But here I am telling you that no, you don't need to look for all potential natural numbers. Look among only these three numbers. Okay? That is a huge progress. So now let us check. For n equals to 1, if I want to check n equals to 1, I go back here. I put 1, the left-hand side becomes 2, the right-hand side becomes 2. So that is true. So yes, this is acceptable. For n equals to 2, the left-hand side becomes 5, the right-hand side becomes what? 4 times 2, 8 minus 6. You see, this is not acceptable. Okay, so I have to take this off from my list. N equals to 2 is an answer for here, yes, but it is not an answer for this one. And it is not surprising because this one is not reversible. Okay, and what about 3? So if I put 3 here, it becomes 9 plus 1, 10. If I put 3 here, it becomes 10. That is also correct. So yes, that one is also correct. So finally, I was able to show that there are only 2 natural numbers for which this works, and those are one of them 1 and the other one 3. Okay, I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.